final session of three wonderful talks. First by Mike Gehm of University of Arizona.
So I'll also start by thanking the organizers for the invitation and all of you for sticking around to the bitter end. And now for something completely different. So spectral classification sensors and adaptive approach. This is work done in my lab at the University of Arizona. LENS, the Lab for Engineering Non-Traditional Sensors, our group focuses on designing and constructing optical sensors of various types that are sort of out of the ordinary in terms of the way they approach making measurements. Before I go on, I need to acknowledge that a lot of this work is due to the fantastic efforts of a bunch of really talented postdocs and students. Okay, so today I'm going to talk about physical sensor approaches, some simulation, actually some hardware, for directly performing classification in spectroscopy and spectral imaging. These devices I'm going to talk about work through adaptive measurement design, which can be viewed as sort of sequential design of the measurement matrix or the sensing matrix, one row at a time based on what we've learned from the previous measurements that we've made so far. So just so we're all on the same page, remind you, optical spectroscopy, we're looking at the electromagnetic power spectral density as a function of frequency or wavelength. It has value because the physics of the light-matter interaction carries information about the matter into the light field, so we can learn about the matter that the light has interacted with. And typical spectroscopy has, a couple hundred, maybe as many as 10,000 spectral channels. Spectral imaging is a generalization of intensity image, where instead of having a brightness at each spatial location, we go ahead and we acquire a full spectrum. And so the whole thing is called the spectral data cube. And typically you have maybe 100,000 to 100 million elements. So definitely, at least in the naive basis, very high dimensional data. Okay, so unlike imaging, nobody really has a drawer full of spectrograms that they've taken and they store for sentimental reasons. So spectroscopy is almost entirely done not for the spectrum itself, but for some type of end product that you're going to do with it, some type of exploitation that will be run on it. Detection, classification, concentration estimation, what have you. Classification is a very common task, and it's exactly what it sounds like, matching a set of measurements. So a noisy spectrum here on the left, and looking at a library and saying, oh, well, that's clearly number 2. Of course, that's easy when the noise is low. And so here you see I've superposed the measurement on top of the library, and it falls very neatly on the green one, so you can tell which one it is. Of course, we can think of the library as vectors in some high-dimensional spectral space. And then, of course, it's real world, so there's noise. So we have little noise bubbles that live at the end of those vectors, and our real instantiations are drawn from somewhere in that bubble. So again, when the bubbles are small compared to the separation, it's easy to classify. But when the bubbles get a little bit larger, all of a sudden it becomes a little bit harder to tell which one you're looking at. Or now the bubbles dwarf the spectra. You can't even see the arrows in the middle there, and it looks like just noise. So again, the thing that really describes how hard it is to do spectral classification is this ratio of the separation to the noise that you're going to get in the measurement. And so we define something we call the task SNR, TSNR, and it's just the ratio of the minimum Euclidean distance in the library to the noise standard deviation that you get when you make a single measurement. Other definitions are certainly possible, but this captures sort of the basic concept, and then we convert it into a dB basis. Just so you can put some real numbers for these cases, 25 dB down to minus 25 dB. I'm going to be showing you simulations and experiments going as low as minus 50 dB. So the measurements are going to look like pure noise. Okay, so because of that, because the low TSNR situations, which frankly are the ones that you really care about. If you're trying to detect something nasty, you really would like to detect it when there's not much of it around. Or you want to detect it very quickly so you don't have a lot of time to sit and make measurements. So, and frankly, the problems where it's high SNR, that problem's already solved. People already have solutions that work very well. So it's the low TSNR situations that are of import. And you're unlikely to actually make a successful classification after one measurement. So we need some kind of decision framework, and we're just going to use sequential hypothesis testing. So sequential probability ratio test. So we keep track of the probability ratios of different hypotheses given the measurement history, which has a nice update procedure with respect to the previous version of that ratio and the probability of the latest measurement that you get given the different hypotheses. And you track that ratio, and when it crosses a threshold above or below that are determined by your acceptable false positive, false negative rates, you stop the process. You say, okay, I'm ready to make a classification. And you go on. In the multi-hypothesis case, where we have more than 2 things in our library, we track all the pairwise versions in a matrix form, and we stop once a single hypothesis is the winner against all of its competitors. Okay, so that's how we're going to make decisions, making measurements. So optical, in the optical field, as long as we're not photon limited, we have a very unique opportunity, or a nice opportunity. And that is because in that situation, our noise comes post-measurement. It's from the transduction and the ADD of the photodetector. So if we can make projections optically, this actually has a noise benefit to us. And so hopefully this is all very obvious, but let me just walk through it real quick just so we can sort of wrap our heads around the game we're trying to play. So 2 spectra in spectral space, and sort of the canonical way to do it, normal spectroscopy, we measure it in the Dirac or spectral channel basis. Each measurement gets a noise uncertainty, so we have an expectation, but each one has a fuzz, and that fuzz is of the size that we get from the transduction and the aided ADC process. So then if you're going to try and discriminate between these two, you're going to synthesize onto the optimal direction, which for 2 vectors is the difference between them. And in doing that synthesis, you have to add that noise and quadrature. So what you're left with is a measurement where you have this separation of the expectations, but you have this noise fuzz. Whereas if we do the projection optically before transduction, then we project into the same direction, we get the same separation of the expectations, but the noise fuzz is smaller. Okay, so doing the projections optically is a win. Of course, we're actually not limited to projection onto unit vectors totally. We have a little bit of freedom over the norm of our projection, the magnitude of our projection vector. Details which I won't get into, but essentially the maximum advantage, the maximum length is root n. So that potentially gives us some separation advantage of the expectation. So same direction, but the blobs are a little bit better separated. But of course, we have the possibility that we could project into a wrong direction, and that has a separation penalty. They come closer together. And so the upshot of all those pieces is that design of the projections is critical. There's a limited upside from multiplexing. There's no limit to the downside from being in the wrong direction. So what you really want to do is you want to find the direction that gives you the best balance of those 2 factors. Okay? All right, so fine. We've got a sequential hypothesis testing framework. We're going to design our features. How are we going to design them? So I said for 2, the optimal direction is the difference, but we've got a cluster. Okay? So one obvious approach, ad hoc approach, would be to imagine a PCA type solution. So here's our spectra in our library, and the first principal component, of course, is the direction that maximizes the variance. It does a reasonable job of spreading them out in that direction. So that's a good first attempt at a separation direction. And so that's great. So we at least have a method by which we can start to think about how to find a direction. But the sequential probability ratio test is giving us probability estimates of the hypotheses as we're going along. We might as well be incorporating that information as well. So what we do is, instead of the straight PCA, we do like a probabilistically weighted version, which is just the eigenvalues of the intraclass scatter matrix. And when we do that, so there's the cloud. We make our measurement. A couple of them remain really highly probable based on that first measurement. Others have become less probable, and this eigenvector now pulls out the direction that tends to maximize the variance of the ones that are still floating around that we're still worried about. So that's going to be the framework that we're going to use to design these features. So we put them all together in the system that we name the system that has all of these together, the adaptive feature-specific spectrometer. I'm showing you some initial simulation results here for a 5-class problem. So it's one of 5 possible spectra. We're using pharmaceutical spectra, 1,300 spectral channels, and we do a bunch of Monte Carlo runs and the like. And the red curve is for a traditional spectroscopic instrument, where basically you've made the measurements and you've tried to synthesize these features post-measurement. The blue is where you're making the optical projections, and you're changing what those optical projections are adaptively based on your best estimation of what's going on. And what you see is 2 things. We have a there we go. We have a 2x penalty that we pay in the high task SNR limit. That's really just an artifact of how we implement things. The PCA approach gives us plus minus values, and we can't make negative light. So we measure all the positive components. In one measurement, we measure the negatives, in another, and we subtract. And so any measurement we choose, any feature we design actually requires 2 measurements. In the high SNR limit, we could probably just make one of them and go ahead and make a decision. It would probably work fine, but you know, the 2x is just up there to sort of show the details of that. But in the low SNR limit, we see an improvement of about 150x in the mean time to classification. And this is potentially a very important way to slice the data. Again, a lot of applications where you're trying to classify stuff, it's very important that you make an accurate decision as quickly as possible. You know, whether it's a pathologist trying to screen something, or you know, somebody trying to detect some type of hazardous material, or what have you. So, okay, great. Simulation seems to show that the idea is reasonable. How would you build one? Well, this is a traditional, sort of how a traditional dispersive spectrometer works. The light comes in, hits a dispersive element, gets split into a rainbow, and it falls on an array of detectors, and they make all the measurements in the different spectral channels. If we instead replace that detector array by a micromirror array, a DMD, then what we can do is we can direct certain channels onwards and block others. And so we end up with a weighted version of the spectrum coming off of the DMD. We then collect all that light and put it onto a single photodetector, and that physically implements our projection. Okay, and the projection, the feature is the pattern of the mirrors implemented in the transverse direction on that mirror array. So we built it. So this one, there's some limitations in terms of the hardware that we could get easily. Right now we're going to limit ourselves to on-off switching only of channels, although again there's really nothing that would fundamentally keep you from weighting the channels with grayscale type stuff. And the size of the array we have about 160 spectral channels. So we redo the simulations for that. The experiment, rather than get all the pharmaceutical stuff together and do all that, we just had some LEDs. We had some RGB LEDs that we could basically create different libraries of spectra with. We simulate it, and then the pink dots are actually measurements made on the apparatus. And you see that the experimental data falls really nicely on our simulation, validates that we're probably doing a decent job with the simulation. Again, we see the 2x poorer on the right, again, just an artifact. We see 15x improvement on the left in the low TSNR. So you say, wait a minute, when you showed me the simulation for the pharmaceuticals, it was 150x, now it's 15. What's going on? Well, so there's a couple of possibilities. It might be something about the spectra themselves. Do the pharmaceuticals have a lot more detail? They actually do. They're a lot more complicated looking, at least, than the LED spectra are, which tend to be smoother. But again, they were also 1,300 channels long versus about 160. So the first thing we tried was just take the pharmaceutical spectra and downsample them to the same length. They still retain a lot of their structure. The structure doesn't get smoothed out in that amount of downsampling, but when we do it, what we see is that the pharmaceutical results now essentially fall on top of the LED results. So it looks like it was really the dimensionality that was the driving factor in the change in the improvement that the system is observing. And in fact, then we can take the pharmaceutical data and we can downsample it to all kinds of different sizes, and we see that the gain goes essentially linearly with the size of the dimension of the problem. And we haven't really figured out exactly why that's the case yet, but that's something that we're trying to wrap our head around. So all of this has been going on over various pieces of it over the past couple of years. We finally tied a bow on it, and it came out earlier this year. If you're interested in more details than I can provide in the time here. So question number one, is adaptivity worth it? Right? Intuitively up front we said, yeah, it seems like design shouldn't be important. This is again the pharmaceutical simulation. Now I'm including random features. So we're projecting onto just random features. So we're getting the multiplexing, and what you see, though, is that we must be paying a huge penalty for projecting into the wrong direction. So we're seeing only a gain of about a factor of 2 with random projection. So we're giving up almost all of the multiplexing gain that the optical projections give us because we're projecting in the wrong directions all the time. Let's see. Yeah, so about a factor of 75 difference between random and the design features. So definitely seems like it's worth it. Okay, so the PCA, very ad hoc. There's no reason to suppose it's optimal. It doesn't take into account any knowledge of noise. And in fact, if we go back, we fully believe that what's going on here, notice we end up tracking parallel to the traditional instrument. We are using features that are essentially ignorant of noise, and the signal has gotten so bad that the system is basically averaging at that point. So basically, we believe that the adaptivity in the design has just delayed the onset of averaging. Basically, when you have to average to get more measurements to get improved performance. So what we've been looking at is an information theoretic approach that will allow us to find the feature that gathers the most information each time. And people have looked at information theoretic design before. They usually look at the mutual information between the source and the measurement. And what that does is it optimizes the system for high fidelity. Now, high fidelity may be a decent analog for system performance, but there's no reason to expect that it's identical. Okay? And so one of my colleagues at the University of Arizona, Mark Neifeld, formulated something called task-specific information and showed how to calculate it tractably. And this is the mutual information between the task answer, the answer to the thing you're trying to accomplish, and the measurements. It's just the mutual information between those two things. This is the first of many papers that they had on it. But so that's the thing that's really trying to find the feature that's best at what you're trying to do, rather than the feature that's best at giving you a high fidelity reconstruction or a high fidelity measurement. And so we started to look at this, using this as a framework. So now we have to optimize TSI, this mutual information, subject to the physical and system constraints. So physics, first of all, is going to constrain us that our projection vectors, the elements of them have to be in the domain 0 to 1. We can't make negative light, and we don't amplify light. We can only let some fraction of it through. Our actual system, the implementation that we're currently messing with, is more restrictive than that. We only allow them to be elements, either 0 or 1. Okay, we don't allow fractional, again, although that's certainly something that we could build, we're currently not. So grayscale, optimizing that represents essentially the surface of an n-dimensional hypercube. And then the binary case is optimization on the vertices of the n-dimensional hypercube. Of course, exhaustive search for practical problems is impossible, so we have the issue of some type of optimization, which introduces the possibility we're going to get stuck in a local maximum. For the binary case, what we do is we use a nearest neighbor hill climbing on the vertices. So here you see a graph representing a 4-dimensional hypercube, just to keep it comprehensible. We have a starting code word that we believe might be a good place to start. We compute the TSI of its nearest neighbors, find the one that has the best TSI, use that as the new starting point, and move on. And we do that until we stop seeing improvement. And obviously, now we're only ever looking at up to n instead of 2 to the n vertices at each as we step through it. So it's something that we can actually do. So, first simulation of the AFSS with TSI, artificially small problems so that we can actually do exhaustive search. So it's 2-dimensional up to 7-dimensional, okay? So very few spectral channels. The solid, let's see, make sure I get this right. The solid lines are the PCA, the probabilistic PCA, the scatter matrix, and the dashed lines, which you can barely see, are TSI. They're below, and we see that about a 4% improvement in the cases where we can do an exhaustive search. Okay, so now let's go to higher dimension, more practical problems. So now we have to do the hill climbing. Maybe we're not finding the absolute TSI optimum, but again, we tend to see about a 4% improvement. It's a little bit disappointing, right? We would love there to have been a lot of win, but sort of the half glass full way to say that is it means that this probabilistic PCA is potentially a fast TSI approximate. We can use it, and we're not missing a lot of what's on the table. Okay, And it's definitely far easier to compute than the mutual information, the TSI stuff. So obviously we're going to be digging into that a little bit further. All of this is the TSI stuff I've shown you is for simulation. We actually have some experimental results. They also confirm a few % improvement, but there's some quantitative differences between them and simulation that we're trying to iron out. So I'm not really ready to show those yet, but they look like they're going to end up confirming these simulations. Okay. So that's adaptive spectroscopy. Remember, way back at the beginning, I said, well, we're also going to look at spectral imaging. So we have a hardware architecture in the spectrometer that allows us to implement spectral filters at a single spatial location, the input aperture to the spectrometer. How are we going to make that work for many spatial locations in parallel? A parallel array of those instruments is not a practical solution, so we're going to need some other kind of architecture that still gives us the freedom to do that kind of stuff. And so with that, a blast from the past. This is actually an architecture that I helped develop when I was a postdoc in Dave Brady's group, and actually the publication was done with some help from Rebecca Willett as well in the reconstruction. As far as I know, it was the first compressive spectral imager created. And the architecture implements, I'm not going to walk through the whole thing, but basically it makes a rainbow. It punches holes in it with a mask, and then it puts that rainbow back on top of each other. So spatial locations at the end are preserved. A spatial location in the input falls in a single spatial location on the output, and the net effect of all of this is to create spectral filters at each location. So this is getting close to what we want, right? We want adaptive spectral filters at each spatial location, but this is static. And so what we're going to do is the goal is to replace that static mask with something adaptive that will allow us to change the filters. And this, again, is just showing how you end up making those spectral filters on each spatial location. The upshot is, though, it's not a free ride, okay? It's actually very hard to make different spectral filters at each spatial location. This does a great job of it, but they turn out to have some interrelationships, so they're not completely arbitrary. Let's see if there's any, yeah. Okay, here, so this is how the filters end up being related. If we look at a single a row of spatial locations in the scene, or a row of spatial locations on the detector, and we label them with letters, so this is location A through and so on, and then we look at the corresponding row in the mask that's going to get used to make these filters, and we number the code elements numerically 1 and up. What happens is that architecture, the first however many spectral channels you have, that many code elements make the feature for the first, make the spectral filter for the first spatial location, and 2 through 1 more on the other end make the spectral filter for the second location, and so on. So you get this sort of cyclic permutation of the elements of the spectral filter. So they're not completely arbitrary. You're stuck with this interrelationship that you've got to work with. And so now we have to optimize the TSI of an entire row jointly. So what we need to do is we need to design the mask pattern on a row to maximize the TSI of all the locations in the row. And so we call that vector TSI, except we only want to count the ones that we haven't classified. If we've already, remember, this is an adaptive process, some of these will have decided already. And so we don't care about making a projection that is good at distinguishing them because they're already done. So that's what we're, vector TSI. Now, we're not quite to the point where we're doing all that. There's some limitations to our current simulation and implementation. Again, it's a 0-1 mask only. So again, we're on the vertices rather than the surface of the hypercube. And instead of doing the full optimization across the row, we're just going to optimize TSI at sort of a few locations scattered across it. And that's really just for computational reasons so that we can sort of get some initial intuition faster. Because again, these computations are pretty time consuming at this point because we haven't spent a lot of time optimizing the computation algorithms. But with that said, we've started to look at how this kind of approach would work. So we've got a framework. Now we need an input source. And so we need some way to give spatial, we need a source data cube where we know what spectra are at which locations. And so what we decided was we just take a scene, in this case Van Gogh's Starry Night, and we convert it to grayscale, and we posterize it to the number of grayscale levels equal to the number of compounds problem that we're going to try and solve, and we assign a different spectrum to each of the grayscale levels. So this is a 5-level posterization. So we assign, so black gets this pharmaceutical spectra, this gray gets this one. There's actually 5 of them, and there's the full library with the 5 different values. Okay, so again, the spectra have nothing to do with Starry Night. People always ask, are you measuring the paint or something? You know, we're just using that for spatial structure, something that has interesting large and small scale spatial structure. And then we assign other spectra just based on the shading. It's just an initial starting point. Obviously, we'll move to real spectral data cubes eventually. Well, we've got a simulation running. Let me walk you through the different pieces. Here on the left, here's the scene. Upper left is the scene. So these are the 5 different compounds that are scattered throughout our scene. Over here, we're going to see the number that we've classified after each measurement, as well as the number of errors we've made. This is the mask pattern that the system is using. What the detector sees in the middle of the bottom, and then the pixels that we've classified at this point in the bottom right. So this is actually after the first measurement. So we've designed the measurement using this TSI, this pseudo-optimized TSI version I've already warned you about. And we've classified about, it's hard to see, but maybe about 9,000 of the 65,000 spatial locations already. Measurement 2, that jumps to close to 20,000, I guess, with about 220 of them incorrectly classified. The mirror pattern's becoming more complicated. We're starting to hone in on stuff. You can see more pixels popping up in the final classification structure in the bottom right. Measurement 3, measurement 4, 5, 6, 7, 8, and 9. And this is all done at 0 dB. So the noise, the measurement noise, is on par with the separation of the signals in the library. So after 9 measurements, we've classified about over 60,000 of the 65,000 locations in the scene. Now, 9,000 parallel measurements, right? We're actually using 65,000 detectors in this structure, but 9 sort of exposure times. We've classified, so an average of 9 measurements per, or a total of 9 measurements per location. We've identified the different compounds, and we've made about 1,000 errors. So about 1.5% of the locations are misclassified at this point. So some of the trends I can show you here. Very, very preliminary stuff. So again, this is the pharmaceutical spectra, mapped to Starry Night. The blue is for the adaptive spectral imager, and then the green is, again, with just random mask patterns. We observe about a 30x improvement over random. And then on the bottom, the red curves are different kinds of traditional spectral imagers, from tunable filter, push broom, and whisk broom. And there we see improvements up to about 100,000, factor of about 100,000 in the speed at which you would classify all of the locations. So where are we going from here? So to wrap up, design of features definitely provides a crucial performance advantage, especially in the optical domain, where we can make these projections before the noise is added. If prior information is limited, having adaptivity, allowing adaptivity, of course, allows you to learn and develop better models as you're going along. And we see these multiple orders of magnitude improvement in the time to classification. Where we're going next is this last part. We want to have the real full vector TSI. We're building a prototype. We're already doing the optical design of all that right now, and so hopefully, next time I'll be able to show you results that have experimental data as well in the spectral imaging. And then what we want to do is, this is part of a 3-tiered process as part of a DARPA KeyCom project. So we're starting with classification. The next phase is end-member detection, which is basically concentration estimation, where you're forced to learn the library as you're going along, and then finally full reconstruction. Those last 2 are going to require different optical architectures, but we want to see how the adaptive approach to measurement design fares in those different areas. And with that, I'll stop, and thank you for your attention.
Questions for Mr. Gehm?
What do you mean mixed? You mean multiple compound mixtures? Yeah, so that's basically that's the end member detection is trying. So that's I don't have any great intuition, but that's essentially the next problem that we want to tackle. Yeah. That one does have a slit entrance aperture, yeah.
And what you're calling the baseline is the slit aperture with one spectral channel on the detector then, or when you compare it with traditional spectral?
The traditional is a slit dispersive spectrometer, so you have the full, all of the detectors. And you're not counting multiple, you're not taking a penalty. You're not, like 100 spectral channels does not cost you 100. It's exposure times.
How can it be worse to measure everything? If I have a
Be-
split
be-
detector,
Because of the noise penalty and the multiplexing gain that you don't get in a traditional instrument. When you have to synthesize, in the low noise stuff, when you have to synthesize onto the
you're claiming optical combination is better than electronic combination?
in the low SNR limit, because you take a single noise hit instead of all of the noise hits on the different channels, which you then then get combined together when you're synthesizing the feature.
So it's additive noise on the detector?
It is yes, it changes. That's what I said. So it completely changes when you're not photon limited. There's different statistics. Yeah.
But is that true of your detector? I mean, if you did put a detector there,
Yeah. We have traditional experimental measurements, and they match the simulation.
would you replace the DVD?
Yes. Yeah.
DVD with what?
Well, actually, no. What we can do is we can just turn on one set of mirrors, and we use the same photo, and we sweep it. So we measure the photons that are falling there. Yep.
Great, Art.
Thanks.
This talk is, Patrick Wilk from Harvard.
Yes.
No, we want to hear what Mike said.
Yeah.